look for a tool that's called class boundary. I found it right here. And again, load all the 7 scripts. And you could double click each one of them, or you could directly just use the wildcard and press add, and they're all here. So we want to do 2 different things now. First, we want to make a different file for each single script individually. And we want to output that in the shapefile format. We also want to show, so in this case, now we just want the boundaries. So we're not going to click holes in this way. Then when we get into the other one, and then we're also going to visualize the holes. I'm not even sure this data set has any holes. Okay. Important is the output directory. We want to put it in the quality directory. So we just did that in the last step. You can select the directory using this little browse box that you can open by pressing this button here. And then we go up one directory, quality, and we say use current. That's going to use the directory you're currently in. And because I'm now computing a boundary individually for every one of these scripts, I can again run on multiple cores. Later we're going to talk about what this concavity value means, but right now we're just going to leave it at 50 meters. And then I'm pressing run, and I'm checking my command line. So I'm running last boundary on the list of files. Again, the list of files can be seen in this file list. I'm running on 7 cores. Maybe you run on 3, 2, 1, 4. I'm putting it into the quality directory, and the file name will be the same, but it will be a shapefile. Just the name will be identical to the original name. And then I press start. Now on 7 cores in parallel on my machine, it was loading all these scripts, doing the computation of the boundary, and putting them into the respective quality directory. If I go into that directory, I should have a lot of shape files now, in addition to the files we computed before. And here they are, the shape files. Now, yours may look different. Mine have an association to a little program, and I find this little program very useful. You do not need to start ArcGIS to quickly inspect the shapefile. I included this tool here. I didn't write it. It was written by someone else. It's the little shape viewer. You find it in the bin directory. And if you start it, and you look at the help, it was written by Mohammed Hamoud, not by me. And it says, it does exactly that, easily views shapefiles. So then you can go to that directory, area 0, quality, and here you see all the different shapefiles we just computed. These are all describing the boundary of each of these. The boundary of each of the class files. So, remember that was one of the questions. How do you compute a shapefile that how do you generate a shapefile that describes the boundary, a polygonal boundary around the LiDAR points. That's how. But I want to teach you a bit more how to do something else. Now we created one for each file individually. But sometimes you want to say you get a whole bunch of files, like one slide comes back and it's 10 strips, and you want to compute a boundary for all of them. In this case, there's one option. You can always merge files into one on the fly. There's no need to actually merge them and create a copy of the file on disk, but they can be merged on the fly. When it's merged on the fly, it looks like one file. It's like one big LAS file or one big LAS file. So there's no chance to run on multiple cores anymore because we have only one file input. That's why it's automatically grayed out. So now the output I want to call, I'm going to call it boundary dot KML. I'm creating something different now. I'm creating it. Oops, sorry. Boundary dot KML. Boundary.kml. So I'm choosing as the format a KML format. Now for the KML format, the nice thing is you can display it in Google Earth, so you can just send it to your friend, say, look, the cool LiDAR I collected, or I'm working on, it's right there. It doesn't have, then the LiDAR isn't being sent, the LiDAR is very expensive, but you can communicate easily to somebody where you have LiDAR. It's also a good way to share the LiDAR data, the coverage of the LiDAR data, when you're not allowed to give the LiDAR data. You can say, well, at least I can tell you where I have LiDAR data. This time we also want to show the holes. Also, I'm not sure this data set has holes. It is important, however, if you want to use KML as an output, you need to know the projection information, meaning you need to know where the LiDAR data is on the globe. And these particular LAS files, they don't have projection information. And that often happens that you get LAS files and they do not have projection information. I happen to know the projection for this, and we can edit again on the fly by using this projection tab. So now we use filter, we use transform, now we're using projection. Projection can add a projection that you know that is missing, or you can override one that is wrong. And I know this is a UTM projection. And I know it is on the northern hemisphere, and it's in the zone number . Is it 19 or 17? I need to look at my sheet sheet. I think it's 19. Get 17 or 19. Typical. That was prime numbers. Oh, I know where it's written. It's in, yeah, wherever it's in the document, in these tutorial documents, because it uses the same data. So the exact same data is used in these tutorial documents. And I'm pretty sure I see it somewhere here. 19. Yeah. So it's 19, not 17. So that's where you can go afterwards when you come back and you don't, or you want to teach your colleagues, in your school. You got tutorials that do exactly the same thing we do today. So I go back to last boundary and I use zone 19. I think that is all. Again, for your reference, I merged the file into one, I gave it a file name, and I chose the KML format as output, and I used holes, the optional holes, to also show interior holes. Now let's just read the command line. So, last boundary, that's like always, list of files, same file list as here, but now that new command, we merging them, and we gonna compute the holes that are inside. The output again goes into this directory, but now it's output into one file, not one file for everybody, for each individual script. And we're using the UTM zone 19. Okay, looks correct to me. Have a look what we produced. Mine is already done. I go into the directory quality, and there's now the boundary.kml file. And let's see if my internet connection works today. If you have Google Earth and if you have internet, you can try to do the same. Yeah, there we are. So that's where I have the LiDAR data. Now, very nice, very clean, very easy to understand. This is the area where we are operating. Okay, so now I showed you how to create. And you can also do that, of course, for every tile individually. You could now have 7 KML files. If you didn't press the merge button, you could make 7 KML files. And then you would have them all individually. Okay. Next thing we will do, we will use last overlap to create these overlap images. So this is all part of the quality checking. So last overlap. Now be careful, there's a tool called a very similar name called last overage. Or last, you may think it's called last overage. That does something very different. So last overlap and quality checks, lifetime overlap. So by now that should be almost a routine. We go to area 0, strips raw, and we're adding all the strips. Then we pick in our output directory. Again, I would like to pick the quality directory. Say use current. Like before. In this case, we will leave all the default values like they are. That means we will create output grid rasters with a step size of 2 meters. We will create color-coded ones where the colors show us where problems may be, or you can also, we create color images. There's also the option to create rasters containing the actual values. So instead of a color blue, meaning 1 overlap, it will be a raster that contains a number 1, telling you there's 1 overlap. These can be useful for subsequent statistic computations, because you can't do that. But for just looking at it, getting a visual inspection, creating the color-coded images is nicer. I want to give it a file name, and I will call it overlap.png. And I say run. As always, a quick sanity check. Class overlap, list of files. Correct. It merges them again. In this case, by the way, I forgot to mention this. In this case, our files are flight lines. So it's important that this is checked. Sometimes you do that same check using tiles. It's already tiled. It's already flight lines that have been tiled. Then you don't have flight lines. Then you must uncheck this. Only if you have the original flight lines that are actually overlapping in separate files, then you check this. We are checking the elevation value, and we are always looking in every 2 by 2 meter cell. We are looking at the lowest elevation value. So that's what this actually means here. And this, for the overlap, we just look at the overlap. We look at how many points from every flight line fall into every 2 by 2 meter cell, and then we look how many flight lines cover every cell, and then we color it differently. That's fairly easy. The other raster, the difference raster, maybe you remember there was this difference raster. The difference raster also takes all the points falling into a 2 by 2 meter cell, and then it looks at the lowest point of all of these points, and it looks at the lowest elevation, so that's the Z value, for every flight line, and then it computes the differences between the different flight lines that fall into the same cell. So if different flight lines are in the same cell, it looks at their lowest value from all the flight lines and computes the difference. And if this difference is more than half a meter, it becomes dark red. If it's a negative difference, meaning sometimes the flight lines are on top of each other in the other direction, it's blue. Blue to red. Both are bad. One is negative bad, one is positive bad. And this specifies when you want to turn them red. If I make this value small, like 0.2, then if I have a 20 centimeter difference, it will already be red. If I make it bigger, like 1 meter, then I'm visualizing only very big differences. Here, it may be useful sometimes to create the actual values and then afterwards create a histogram of the errors from the actual values rather than just a visualization. But for a quick quality check, this visualization is really useful because you have a bunch of flight lines and sometimes you have one flight line that is the mathematics went wrong and the flight line is like this. Yeah? It's completely wrong. This will very be obvious in this visualization. You can pick it out right away. But if you just look at the LAS point clouds, it's, yeah. So this, well, let's just start it and see what happens. Oh no, oh no, what did I do? Don't start it. Did you start it? Anybody started it already? Unstarted. I forgot to specify the projection. So let's do it again. I'm just saying run again. And I again forgot it, but I know I can type it right here. Minus UTM space 90 N. N doesn't mean north. N means everything N, O, P, Q, R. There's some kind of letter code for the UTM zones. Everything N and higher is northern zone, including S, and everything M and lower is southern part of the hemisphere. So when you want to go to Australia, you can put M here. Then, yeah. So N and S doesn't specify north and south. N and S are both in the north. It's a bit confusing. I was confused by that too. Either way. You're in the Philippines, so most of the time, just put the N. It's the same thing as before when you press start. The only difference is it now uses the projection. And when it uses a projection and creates a PNG file, it will automatically create a KML file. And that is sometimes nice. I can close this file now. I can now go to my quality folder and look for what I just created. I created these images, but I also created a corresponding KML file. So I can look at it in a geospatial context. So voila, here is my modern art piece. This is the overlap image. Now, is this overlap good or not? That is up to you to decide, and you must look at the specifications. It is certainly not good if in the middle there's an area where it goes down to, where there's nothing. Then you have a problem. But even if it's covered everywhere, depending if the specification says you have 100% overlap, 100% overlap, I would not be allowed to have any blue. Because 100% overlap means I have at least 2 flight lines everywhere or more. But often you only have 20% overlap and between the flight lines. This was a test flight, a very old test flight done by LiDAR, I guess. That's why it's right next to an airport. There's lots of LiDAR surveys of airports because people usually use these small airports to test flight. There was another image called overlap and the difference image. And the difference image shows you how well the flight lines align. And in this case, it computed for every every 2 by 2 meter area, it computed the difference between the lowest elevations on the different flight lines. And this is the tarmac area. And in the tarmac area, you want this to be mostly white. We chose half a meter, meaning saturated red. So, or saturated. So this is a difference of more than half a meter plus, half a meter minus. But this here is forested area. And in forested area, you can't really use this for the quality check because you don't know if every LiDAR return went all the way to the ground. So sometimes it gets stuck here, sometimes it gets stuck here. So it has nothing to do with the quality of alignment, but it has to do with the different penetrations. However, in the open areas, that's where it really matters. Whenever you have flat open surfaces, they are supposed to be mostly white. And this is a quick visual check. For a more rigorous check, you would compute the actual difference values, and especially in the open areas, and then look at the distribution of errors. I think in this case, this was a survey done quite a few years ago. The scanners weren't quite so good then. This was a very good scan because it had only slight misalignments here. And here's again. There's grassy patches, and here you see little shrubberies, but on the main runways, it's okay. Around houses or buildings, here we have buildings. This is a building. Again, the roof is supposed to be more or less okay unless there's air conditioning units and stuff like that on top. But along the edges of the building, you have you often have very strong red or very strong blue. And that can indicate a mistake. It can also not indicate a mistake at all, but remember the scanner is looking from a slightly different angle. So the one flight line sees the building from this side, and one flight line sees the building from this side. So if there's an edge, this scan hits it here because it doesn't see the area here, and the next one can see all the way to the ground. And then they have basically the height of the building as a difference in that particular 2 by 2 area, meter area. Okay. To do a real quality check, where you can make very good judgments about the quality of the LiDAR data in respect to the reality. Now, how is it real on the ground? You need ground control points. And for this, there's a tool called LASt control. And if we now go to look for that tool, LASt control. Again, I'm loading all the strips. And oh my God. I think we need to see the LiDAR doctor, because our LiDAR strips have the measles. So it looks like. No, what happened, in that directory there's a file called control points or cps.csv. And when this file is there with that particular name, and that's the name I always choose.